Hello, we're live. How are you, Laura?
I'm doing really well, thanks, Ramon. How are you?
I'm good too, thank you. Good. Yes, I think the last time since you and I did pair programming, I've moved, so I'm in
That's
a
right.
different location now.
Yeah. And it's good?
Everything is fine. Everything's chill. I'm very strategically in the corner, so it's not a complete mess. So it's only
Magic
partially.
of camera angles.
Pretty much. Yeah, very much so.
Yeah. So, welcome everybody to our second streaming event for this implementation of Conway's Game of Life using Rust and WebAssembly and displayed in a browser via JavaScript. Ramon and I are both new to WebAssembly, and so we are learning in public together. And you are joining us. Thank you for joining us. We're so happy that you're here. So last time we only got through the setup and hello world steps of this tutorial that you can see on Ramon's screen. So we got through I guess let's give ourselves some credit. We also got through the introduction. We got through the why Rust and WebAssembly and the background and concepts and what is WebAssembly. We did those sort of briefly. And then what we did not even slightly briefly was the setup. We went through lots of steps with the setup. We had things that went wrong and we figured out how to fix them live. And we're going to be doing it that way again too. So things may go wrong and we will figure them out and we will all be fine. So we did the setup and we got through Hello World. We tried couple different ways. We made sure that we could try displaying strings besides Hello World. So we actually got up to, I think it was Hello Wasm pack. And today we're going to be talking about the rules of Conway's Game of Life for anyone who's not familiar or needs a refresher. And we'll also be implementing the game. So we don't know how far we're going to get with this today. We are not trying to rush through. If we need to do this again in a week or two, we are more than happy to do that.
Absolutely.
So
How
are you all set?
exciting!
Yeah. Are you all set, Ramon?
Absolutely. So, small change of pace today. Last week, Laura drove and I navigated. So this time, I'll be a little bit quieter because I'll be the one driving and Laura will be the one navigating.
That's right. So here we go. Okay. So if you, So if you are already familiar, you can go get some water and some coffee and join us in a couple of minutes. But we're just going to go over a little bit of an overview of how Conway's Game of Life actually works. So the universe of the Game of Life is an infinite two-dimensional orthogonal grid of square cells. So you can just think of this as like your X and Y axis, just like regular graphing in math class. Each of those cells is in one of two possible states. It's either alive or dead. And
How
that's
morbid.
yeah. And we can also think of this as populated or unpopulated, which is significantly less morbid. So maybe we'll try to think about it that way. Every cell interacts with its 8 neighbors. So each cell has 8 neighbors, and those are the cells that are touching it either horizontally, so to the sides, or vertically, so up and down, or diagonally adjacent. So they're just sharing like a corner. And at each step in time, the following transitions occur. So rule number 1, any live cell, so a populated cell, with fewer than 2 live neighbors dies as if caused by underpopulation. So if you have a cell that has only 1 populated neighbor or no populated neighbors, then that cell, it also becomes unpopulated. Any live cell, so that's rule number 1. And then rule number 2 is any live cell with 2 or 3 live neighbors lives on to the next generation. So if you have at least 2 live neighbors, you stay alive and you're going to move on to the next. Rule number 3 is any live cell with more than 3 live neighbors dies as if by overpopulation. So I misstated earlier first for rule number 2, and I just didn't even read it correctly. Because rule number 2, what it actually says is this: if you have exactly 2 or 3 live neighbors. And I misspoke because I said if you have at least 2, but in fact, rule number 3 is contradicting that statement that I misstated, because if you have more than 3 neighbors, then you still die as if by overpopulation. So we're optimizing for our population levels here. We don't want to be underpopulated. We also don't want to be overpopulated. We want this nice medium amount of population. And rule number 4 is any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. So if you are an unpopulated cell, a dead cell, but you have exactly 3 live neighbors, then it's like their population flows into you or something, moves out into the suburbs, as it were. So those are our 4 rules that we have to live by in the game of life. Do you have any questions yet, Ramon?
So far, so good.
Okay. So the initial pattern constitutes the seed of the system. So this is what we're going to be starting with. The first generation is created by applying the above rules simultaneously to every cell in the seed. So births and deaths occur simultaneously, and the discrete moment, the exact moment at which this happens, is sometimes called a tick. So in other words, each generation is a pure function of the preceding one. And each generation, if I'm understanding this correctly, could also be referred to as a tick.
Yes.
So each time we're taking this tick, it's like we're taking a little snapshot. This is how every cell is. Every cell is either alive or dead in this snapshot. And then in the next snapshot, we're going to have applied these rules. So some of the cells will die that were alive, some of the alive cells stay alive, and some of the dead cells become alive. And we will see that in the next snapshot or tick or generations. We have 3 different ways of thinking about that.
Yeah. So we can use those terms interchangeably.
Yeah. And so we are going to consider the following initial universe. Could you scroll for me, please? Thank you.
Yeah.
We have this, what is this? 1, 2, 3, 4, 5 by 5 grid. And we have 3 alive cells in a vertical line in the center. So we can calculate the next generation by considering each of these cells. The top left cell is dead. So that's sort of grayed out. And rule 4 is the only transition rule that applies to dead cells. But that top left cell does not have any live neighbors, never mind exactly 3. And so that transition rule does not apply. So that top left cell is going to remain dead in the next generation. And the same goes for every other cell in the first row as well. But things get more interesting when we consider the top live cell. So that's in the second row in the third column. And I lost my place. Where are we? Okay, so for live cells, any of the first 3 rules potentially applies. So in this cell's case, it only has 1 live neighbor, and therefore rule number 1 is going to kick in. So this cell will be dead. It'll be grayed out in the next generation or the next tick. And the same fate is going to apply to the bottom cell in that center, or the second from the bottom cell in that center row. It also only has 1 live neighbor, so it'll be dead in the next generation. But the middle cell has 2 live neighbors, the one above it, and the cell below it. And so that means that cell is going to fall under rule number 2, and it's going to remain alive in the next generation. Yeah. And the final interesting cases are the dead cells just to the left and right of the middle cell. The 3 live cells are all neighbors of these cells, which means that rule 4 applies. And so these cells to the left and right of the middle, they each have exactly 3 live neighbors. And so that means that in the next generation, they will become alive.
And we have, exactly. And we have an example of it here.
Ooh. And so that is what it'll look like. The grid at almost the bottom of the screen right now is what the next generation or the next tick will look like. So almost all of our cells that were dead in the previous tick are still dead. But 2 of the alive cells are now dead and 2 of the dead cells are now alive. And so that is one round. Oh, I just introduced a 4th term for the same thing. I'm sorry.
All fine. All fine.
Yep, one tick.
Yeah.
So that's an example of how this is going to go.
Yeah, and we've got some examples here of what
Mhm.
it looks like moving. And I like that they have
Yep.
little nicknames like Pulsar and Spaceship. And there's
Yeah.
even these larger ones. I'm going to briefly play this just because it's fun.
Mhm.
Because these become quite large. And, oh, I don't know if the noise is coming through. I'm not going to put it in. But, yeah, and I believe that this is, I'm going to completely flub this, Turing complete, meaning
Okay.
it's possible to run Game of Life inside Game of Life, which is weird.
Yeah, what would that look like? Well, that's maybe for another stream, but
you're navigating. I can try and find it in the meantime. But yes, please carry on.
Yep. Okay. Okay, so we have some exercises now, which I can't actually see because my face is on top of them. Thank you.
Does that work?
Yeah. Okay, so we're going to compute by hand the next tick of our example universe, and we want to see if we notice anything familiar. So I would say our example universe, this is that one we started out with a central vertical line, and now we have a central horizontal line. Do we want to do this exercise, Ramon, or do we want to get to implementing?
I would recommend, if I may, that we take the opportunity to start doing some coding, I think.
Yeah, I think so too.
Yeah.
Yes.
Awesome.
So I used to be a math instructor, and the math textbooks love saying the proof of this will be left as an exercise to the reader. So this is an exercise that we will leave to the watchers.
That's great. I love that. By the way, I did find it. So I'll post that in the chat. Do we have a second to look at it?
Yeah.
It's really fun. So what you see here is some Game of Life stuff, and as you zoom out, because of the way they're constructed, the way they're laid out, you're going to see that it's going to zoom out, and eventually it's going to start to resemble a single cell.
Right. So each cell has its own game at the beginning. Each cell has its own game of life happening within it. And then they're going to collide.
Mm-hmm. So this is programmed, and I'm gonna move it along, if I may. Mm-hmm. You're gonna see that eventually it's using its own rules to write those rules.
Right.
Which I just find incredible.
Yeah.
Sorry.
Yeah, and that's also really fractally as well.
Yeah. Totally.
Yep. All right. Yeah, so let's check out how to implement this. Alrighty. So we have some design choices to consider, as we usually do. The game of life is played in an infinite universe, but we do not have infinite memory and compute power. So we need to work around this annoying limitation. And there are usually 3 different ways that people handle this. And the first is to keep track of which subset of the universe has interesting things happening and expand this region as needed. So in the worst case, this expansion is unbounded and the implementation will get slower and slower and eventually run out of memory. So that doesn't sound super cool. The second option is to create a fixed-sized universe where the cells on the edges have fewer neighbors than cells in the middle. And the downside with this approach is that infinite patterns like gliders that reach around the end of the universe are snuffed out.
Right.
And so number 3 is to create a fixed-size periodic universe where cells on the edges have neighbors that wrap around to the other side of the universe. And so what we're imagining is that the cells on, say, the far left edge also consider the cells on the far right edge their neighbors, and the cells on the top edge consider the cells on the bottom edge their neighbors as well. So it still looks like a 2D situation, but we're actually creating more of a sphere-ish situation. Not even a sphere, it's like a
Mobius strip kind of thing, maybe?
Almost it's a Mobius strip. We're getting all kind of mathy in here. I like it. Yeah, so we're going to go with option number 3. And because neighbors wrap around the edges, so the gliders can keep running forever. So we get all the cool things that come from the game of life.
Awesome.
Okay. Any questions, Ramon?
So far, so good. We're gonna be constructing, say, and I guess we'll be able to define what the size of that universe will be, so that we can then go on to have it be variable later on, I suppose.
Yeah.
That's cool.
That sounds good. Okay, so one thing that we're going to need to consider is that we're going to be writing this in Rust, but we're going to be displaying it in the browser using JavaScript.
Right.
And there's going to be a lot of jargony stuff coming up in here, and then we'll have sort of a TLDR 10,000 foot view of what all this means. So JavaScript's garbage collected heap, where objects, arrays, and that's what DOM, that's digital object.
I think it's data object
module. There we go, are allocated. And that is distinct from WebAssembly's linear memory space, where our rest values live. So WebAssembly has no direct access to the collected garbage collected heap. And that was expected to have changed almost 4 years ago. So maybe it has. JavaScript, on the other hand, can read and write to the WebAssembly linear memory space, but only as an array buffer of scalar values of fixed sizes. So WebAssembly functions can also take and return scalar values, and these are the building blocks from which all WebAssembly and JavaScript communication is constituted. So WebAssembly can talk to JavaScript in these scalar values, and JavaScript can talk to WebAssembly using the scalar values in an array. And that's the basis of their communication. That's their Google Translate.
Yeah, so they have this protocol by which they communicate. Nothing to do with Rust. This is like WebAssembly and JavaScript.
Exactly. So Wasm bindgen defines a common understanding of how to work with compound structures across this boundary. So it involves boxing Rust structures and wrapping the pointer in a JavaScript class for usability, or indexing into a table of JavaScript objects from Rust. So we're gonna wrap up our Rust code, which is not readable by JavaScript, in something that is readable by JavaScript, port it through WebAssembly, and WebAssembly will translate that for JavaScript.
Got it.
Okay. So Wasm bindgen is very convenient, but it does not it does not remove the need to consider our data representation and what values and structures are passed across this boundary. So we can't just put anything in to Wasm bindgen and expect it to be able to work with it. We have to be pretty particular about what data types we can use.
Gotcha.
So when we're interfacing between WebAssembly and JavaScript, we want to optimize for the following properties. And the first one is minimizing copying into and out of the WebAssembly linear memory, because unnecessary copies impose unnecessary overhead. We don't want to be copying too much stuff that we don't need and wasting our time and compute. The second one is minimizing serializing and deserializing. So similar to copies, serializing and deserializing impose overhead and often imposes copying as well. And so if we can pass opaque handles, and that word opaque is going to come up a lot, we're going to talk about that, opaque handles to a data structure, instead of serializing it on one side, copying it into some known location in the WebAssembly memory, and then deserializing it on the other side, the JavaScript side, we can often reduce a lot of overhead. So Wasm bindgen allows us to define and work with opaque handles to JavaScript objects or boxed REST structures. So far, so good.
Yeah. So I'm. This is more of a. Wondering and of course question.
Mhm.
Um, so serializing and deserializing, instead of making copies and sort of referring to it, we helps us define and work with opaque handles. And these opaque handles, could they be thought of as a reference?
I don't know.
I wonder if that's what this means. Yeah, where it's like, hey, I'm me, WebAssembly. I've got the data here that you need. If you
Mhm.
needed JavaScript, just hit me up. So I'm not gonna make a copy and send it to you. It's just like, I'm here if you need me.
Mm.
It's
Yeah,
that
yeah,
opaque
like that.
handle that.
Maybe that's sort of related to that just in time concept where
Right.
we're only processing things at the last possible second, like basically when we cannot avoid processing that
Yeah.
thing, as opposed to processing everything ahead of time.
Yeah. And I
Maybe.
wonder if the opacity of it is like, hey, don't you worry about what I've got in here. I've got it. You need it. Don't worry about how I
Pay no
set it
attention
up.
to the man behind the curtain. Yeah.
Yeah, exactly. So it's just like, hey, I've got what you need. Don't ask me how I got it.
Mhm.
Yeah. Okay.
That's
I get
really
that.
sounding like something someone says. They've got like something in their coat. Mhm.
Yeah, it sounds shady.
It really does. We've got a black market of numbers. All right. Yeah. So, as a general rule of thumb, a good JavaScript WebAssembly interface design is often one where large, long lived data structures are implemented as REST types that live in the WebAssembly linear memory and are exposed to JavaScript as opaque handles.
Right.
So JavaScript calls exported WebAssembly functions that take these opaque handles. It transforms their data, it performs heavy computations, queries the data, and ultimately it only returns a small copyable result. So we're not having JavaScript doing all this heavy lifting because that's
Yeah.
not what it's good for. But it is what WebAssembly is good for, and Java Rust is also pretty good at that kind of thing too.
Mhm.
So by returning only the small result of the computation, we avoid copying and or serializing everything back and forth between the JavaScript garbage collected heap and the WebAssembly linear memory. So we're only processing the absolute minimum that we need to in order to make this work, if I am understanding correctly.
Yeah, I think that makes sense. So it's really the WebAssembly linear memory's got all the stuff it needs, and when
Mhm.
JavaScript needs it for its garbage collected heap, and the garbage collection there does a lot of heavy lifting to make sure that, for example, uh, if you're familiar with garbage collecting, it's like, when you declare a variable. Like when I started working, I was working on something called Objective C, where
Mhm.
if I wanted to declare a variable, and I think C did. Oh, you might have done. You did some C, right?
A little bit, a lifetime ago.
Yeah. Do you remember that? Like, if you wanted to like declare a variable or something, you had to be like, "Hey, I need a variable. Please." I think it's allocate this much memory for it.
Oh, I was in C++ and I think it
Ah,
avoided that.
right,
I think that might
right.
have been included in the plus plus.
Very fair. And in Objective C, I had to do a little bit of that as well. So it's like, please
Mm,
reserve this memory for me, and then like when I'm done with it, I will tell you, and
yeah,
only then
yeah,
will I
we did
tell you.
that in my assembly language class.
Gotcha.
Yep.
Gotcha. Yeah. So I think that's what JavaScript does, and WebAssembly is like doing something a lot more low level, and so it's just minimizing the strain on having two bunches of memory being used,
Mhm.
if that makes
Yeah,
sense. Yeah.
it does make sense.
Cool.
Cool. Okay. So we're going to get started by enumerating some hazards to avoid. So we don't want to copy the whole universe into and out of the WebAssembly linear memory on every tick, so every generation. We do not want to allocate objects for every cell in the universe, nor do we want to impose a cross-boundary call to read and write each cell. I have to process what that just said. Okay, so, right.
We
So we're
don't
not going
want
to copy the whole universe. We're both talking to ourselves here.
to.
Okay.
So if I understood
Right.
correctly, right,
Mhm.
sorry, go ahead.
Yeah. Okay. So we're not going to allocate objects for every cell, and we don't want to impose a cross-boundary call to read and write each cell. And so instead, we're going to represent the universe as this flat array, and it's going to live in this WebAssembly linear memory. And so what was not obvious to me, and is still not obvious to me, why this takes up less space or processing power than copying the whole universe, because we in fact are, because we're
Yeah.
just expressing it as an array. So I
I,
don't
th-
get why this is better. I
I
mean, I
see.
understand why it needs to be an array, but I don't understand why that's using less memory.
Yeah, and it's a good question. I think it'll become clear to us once we implement it, once we do the JavaScript side of it.
Mm-hmm.
Um, but I gave this some thought, and I think part of the reason this is more efficient to have, say, one array as opposed to nested arrays, because you could have like an array of arrays, making
Yeah,
this
yeah.
a two-dimensional one.
Mm-hmm.
It's essentially that uh, allocating, you're not allocating the memory for more arrays. You're only allocating enough. Like you're only telling WebAssembly is like, I got an array. Like there's just one array
Yeah,
involved.
so I get that. The part that I don't get is the sentence, we don't want to copy the whole universe. And then
And
what are we going to do? We're going to put the whole thing in an array. And so we are in fact bringing, I think that it's what's confusing is that it makes it sound like we're not bringing information about the whole universe, but that's not what they mean when they say we don't want to copy the whole universe, because we are bringing information about every cell in the universe. We're
right,
just
but
putting it in this array.
I think it's that out of the WebAssembly linear memory on every tick. So it's like, so the WebAssembly linear memory, so WebAssembly itself, the WebAssembly chunk will do
Mhm,
its own thing.
mhm,
And every now and then JavaScript is going to be like, hey, can you give me a graphical representation of it, please?
mhm.
So it's not really copying the universe out. It's just being like, here you go, a graphical representation. Like, so JavaScript, so the browser would be like, listen, I don't care how you do it, but please
Mhm.
give me this graphical representation. Is my guess.
Okay, so WebAssembly is determining the graphical representation, and then JavaScript is just displaying it.
Yes, this is what I think.
Okay, okay. Because what I was imagining was WebAssembly would pass this array with all of these. We're about to talk about these ones and zeros, and then JavaScript would interpret that array and say, ah, okay, given this array, this is the display that I need to make.
That's what remains to be seen.
Okay, all right. So we'll find out.
Yeah.
Okay, and so we're going to represent this cell as this flat array that lives in the WebAssembly linear memory, and it has a byte for each cell. So 0 represents a dead cell, and 1 represents a live cell, so on and off. And so here's what a 4x4 universe would look like in memory. So where we previously were displaying it as a grid, and in this case it would be like 4 across and 4 down. We're instead representing that grid as this array. And so we've got a chunk in elements 0, 1, 2, and 3, because we're 0 indexed. So we're starting from 0 and not 1. We have the first row of 4 cells. And then in the next 4 elements, so elements 4, 5, 6, and 7, we have the next row of cells. So each of these cells is getting represented, and we would be filling in these elements represented here by these boxes with a 1 or a 0 representing whether each of these cells was alive or dead.
Yeah.
Yep. Okay. And so across the top of this array, we can see the indices. going from 0 to 15, representing so 4 by 4, that would be 16 cells. So this is representing all 16 of our available indices. And so if we want to find the array index of a cell at a given row and column of the universe, we have to use this sort of complicated formula. But spoiler alert, we determined yesterday that we, the humans, are not going to have to interact with this directly too much.
Cool.
So but what it looks like is we've got this function. So we have an index, and it takes in 3 parameters. The index function, that is, takes in these three arguments. The first is the row, the second is the column, and the third is the universe. And the index of that cell is the result of the computation where we multiply the row by the width of the universe, and then we add the column. Yeah?
Sounds good to me.
All right. So we have several ways of exposing the universe's cells to JavaScript. And so to begin, we'll implement the standard format display for universe. And I believe we discussed yesterday that that is in Rust language, we refer to that display as a trait of the universe class. Right?
Struct. Yes. Your
struct. Okay. Yeah. Right. A class is a struct in Rust. I come from Python. Is for context. Okay. So a struct.
Yeah. I don't know if they're equivalent. I think I would be corrected and told why this is different. I think it has to do with how it's instantiated.
Mm-hmm. I'm going to go with analogous.
Oh, I like that. Yeah.
Yes.
Yeah. Let's go with that.
Yes. That can't be wrong. And if it is, don't tell me. Okay, so we can use this display trait of the universe struct to generate a Rust string of the cells, which are going to be rendered as text characters because they're all zeros and ones. So the Rust string is then copied from the WebAssembly linear memory into a JavaScript string in the JavaScript's garbage collected heap, and is then going to be displayed by setting HTML text content. And we'll be getting to that in a little bit. And so later in this chapter, we're going to evolve this implementation to avoid copying the universe's cells between the heaps and to render to this canvas. What is that bit? I mean, it means something, but you know what I mean?
Yeah. So canvas is an HTML element meant for drawing. I'm gonna probably get this wrong. Meant for drawing two-dimensional, dynamic
things.
Content, right? So a lot of time canvases are used for things like games, like drawing apps. I believe Excalidraw, for example, uses a canvas.
Wow.
So it's a quite self-descriptive name. It is a canvas where you can draw. And if you see here, I think this answers our previous question because we're returning a string. So of our two options here, we're either returning a string. So WebAssembly is the front end being the browser, saying like, hey, listen, I don't care how you do it, but please, if you could please give me a string representation of the universe. So there's no copying of the universe involved from WebAssembly to JavaScript. So only the WebAssembly binary is concerned with the universe.
Right.
Sound good?
Yeah, I'm still stuck because I just feel like it can't be true that we're not bringing the entire universe, because we're bringing every cell of the universe, and the universe is composed of these cells. So we are in fact bringing the whole universe, but maybe it's more what's meant by that is more that we're only bringing information about this this generation of the universe, as opposed to any of the other generations, like the previous ones.
I think that's it. It could be. I think the thing that makes it tricky to sort of conceptualize is that yes, we're not copying over that universe we're not copying over that universe struct that we're defining in Rust,
Mm-hmm.
but we are bringing in its contents in one way or another. So
Right.
it's kind of a tongue-in-cheek way of being like, well, I'm not technically copying the universe. No, what we're getting is a representation of the universe. So it's not
Mm-hmm.
the universe, because the
Mm-hmm.
universe, remember, doesn't only contain its data, but also its functionality.
Right. Right. Okay.
So doing things like calculating how many neighbors are around, how many,
Mm-hmm.
what the next tick, doing the tick.
Mm-hmm.
All of
Yep.
that is self-contained in the universe, and
Right.
that we are obfuscating. That's the stuff we
Mm-hmm.
are leaving opaque.
Yeah. Yeah. Okay. That works for me.
Yeah.
Yeah.
Cool.
Yeah.
Cool.
Okay. So let's get to the implementation. So in the
Awesome.
last chapter, we cloned an initial project template, and we're going to modify that project template now, starting by removing the alert import and the greet function that we used
Oops.
in our hello world.
So let's
And we're
start
going
with
to
that.
replace them with a different, with a type definition.
Sorry, I'm just making sure we got space here.
With a type definition for cells. Gotcha.
Yeah, so I'm just gonna make this a bit smaller. I hope the size is okay.
Yeah. Well, I mean, it's good for me anyway.
Folks, if you're watching and it's too small, please always let us know.
Absolutely.
So that's source librs. Yeah.
Mhm. I like your colors.
Thank you. It's a theme called, I think it's Darkula
Oh, yeah, yeah, yeah. Mhm.
or Dracula. I could be wrong. Anyway.
Okay, so we're going to remove that alert import and the greet function. And that alert import is that we use it anyway on line 13.
Yeah. I think that's the importing. Yeah.
Mm-hmm. Okay.
That's gone.
Right. Okay. And then we're using it on line 13 in
Yes.
this greet function. Yep. Okay.
And that'll go as well.
Yep. Bye-bye. Okay, and so we're going to replace them with a type definition for the cells. So we're going to declare the cells, and we have to give them a type. So if you, like me, have spent most of your time in languages like Python and I believe JavaScript, then you may not have needed to define the type of variable that you were declaring. Like if you said something was going to be the number 3, you didn't have to declare that that was an integer versus a float, where you'd say like that's 3.0, and the program would just figure that out based on context. Rust does not just figure things out based on context. You need to be very explicit with it, and so we have to tell it specifically that we are going to be passing particular types, and the way that we do that is by saying the size of the types that we are creating. Do you want to talk about what you've just written, Ramon?
Sure. I would just love to take a moment and say thank you to Jagger for so kindly telling us that this is great. I've just displayed
Yay,
the
hi,
I don't know if
Jagger.
you can see my comment there.
Yeah.
So hi Jagger, nice to see you. Thank you very much. Yeah, let's talk about what we've done here. Because I pretty much copied this, and I like to type it out. It always makes me happy. But if we were to go over each of these, see what we got here. We've got these little comment-like things on top of our enum declaration. So the first one is Wasm bind gen. So from my understanding, sorry.
Go ahead.
Okay, cool. So from my understanding, this is saying like, hey, we're exposing this to Wasm bind gen, which you remember allows us to bring it over to Wasm. This is how we're going to represent the numbers inside our enum. Because you see, we've got a 0 and a 1 to represent dead and alive.
Right.
And this is telling it what kind of number it is. Because in Rust, unlike other programming languages, we got to be specific about what kind of number we have.
Right.
Because in computers, numbers are represented in binary with a certain byte size. So this is telling us this is an unsigned integer of an 8-bit unsigned integer.
Right. Yeah. So that is our type declaration, even though it does not contain the word type.
Yes.
Yep.
And then what we've got here is we're deriving traits.
Mm-hmm.
So we're saying, hey, this enum, we'll get to what an enum is in a sec. This oh no, I think you covered it. Yeah, sorry. This enum can be cloned. This enum can be copied. It can be displayed in debug statements.
Mm-hmm.
And we can check if it's equal to other cells.
Right. Right. So traits, if I'm understanding correctly, in Rust, a trait is like a function. It's a method belonging to this struct, right?
Yeah, I
Like
think so.
an object or an object of this struct. If that object might not be the right an instance of this struct has these 4 methods: clone, copy, debug, partial, equality, I guess. Oh, this is going to have to be 5 methods, and actual equality. So the difference, so we can be partially equal or we can be actually equal. Is that what that means?
Yeah, I think what these let us do, for example, is I'm not very familiar with Rust, so I'm probably going to mess this up. But let's say we have cell one, and let's set that to be cell dead. Right? This is my Ruby showing. I don't even know. I think this is right. Right? We got one cell that's dead, and then we got cell 2, which its value is set to cell alive. So what, for example, the partial EQ and EQ let us do is, for example, oh my goodness, I println, I think. Oh no, I don't know how to do print statements in Rust. The debug one lets us do this. Right? This lets us print out a string representation of that. It automatically gives us the ability to turn that into a string and format it like this.
Okay.
It also lets us do things like cell 1, like if we do, I don't know, if cell 1 is bigger than cell 2, because that's where the partial equality is already leveraging. We're leveraging these traits to be like, hey, you can compare these two cells. If we didn't have those traits, Russ would be like, what are you trying to do?
Okay, so partial equality is in math terms what we would call an inequality, where we say that something is like less than or equal to or greater than or equal to.
I believe so.
Okay.
It could also be, and maybe this is something we'll have to look up as well. But partial equality could also mean, like, if you have you ever done like double equals and triple equals in JavaScript?
I've done, well, so no, not in JavaScript. In Python, a double equals would be like is equal to, and then that basically means that they have the same value, not that they are the same thing, but that they have the same value.
Yeah, and I think that's almost the same. So I think what partial equality could be, and I could be totally wrong on this. Let's say in JavaScript, right? This would give you true.
Okay.
Because the double equals is saying, like, is it, as good as equal? It'll do what's called type coercion to be like, hey, you are a string, but let me coerce you into being a number. But this is triple equals. It's going to be like, oh no, hold on. That's a number. That's a string. These are not the same.
And we can't just use single equals because that's actually assignment.
Correct. Yeah.
Yeah. Okay.
I think the rest applies for like clone and copying. I believe with these you can, create copies of different cells.
Nice.
Oh, sorry. And you know what? I just realized we went through all of that here. I keep doing this.
Yep. So we've talked about that, about the representation, the typing, and that we're setting everybody to be dead is 0 and 1 is alive. And that the reason that we're doing that, and we hadn't talked about this part, is because this way we can count a cell's live neighbors just using addition. Because your live neighbors have a value of 1 and your dead neighbors have a value of 0. And so when you add up all of your 0s and 1s, that sum is also going to tell you how many live neighbors you have.
Yeah.
So that's handy. Okay. And so now we need to actually define the universe. And so the universe has a width and a height because it is 2-dimensional. And it's going to have a vector of cells of length, width times height. So that vector, that array, is going to have, however, the width times the height, that product is going to tell us how long that vector is.
I was not ready to define the universe on a Tuesday.
Indeed. Yep. Okay.
So that vector is the same as an array? Is that right?
I mean, in linear algebra, yes.
Yeah.
And I think that they must be using it, using the 2 words interchangeably in this tutorial because they previously referred to that as an array.
Right.
And they're now referring to it as a vector. So I'm going to go with we're using these interchangeably.
Yeah. I think one is specific to JavaScript and the other one to Rust.
Ah, okay. So is it an array in JavaScript, but it's a vector in Rust?
Yeah, I think so.
Yep. All right, that makes sense. So right now we're writing in Rust. So we're defining everything in terms that Rust will understand. And then eventually some of those we're going to have to translate into terms that JavaScript can understand. But we'll do that later.
Mm-hmm.
All right. So we have our width is it's an unsigned integer, right? It has to be an integer.
Yes.
For this, I mean, it wouldn't make sense to have it be anything else for this context.
Ooh, sorry, we got a comment from Jagger.
Oh yeah.
Oh, whoops.
Spec in this case is a generic container that wraps around native arrays. Something like an array list, something in Java, for example.
Okay. Ah, that's where the generic comes from. Gotcha.
Okay.
So that's where the they're not carets, are they? These bigger than and smaller than signs. Sideways carets.
Yeah, they're pointy brackets.
Pointy
brackets.
I love that.
Thank you, Jagger. All right. So, and then, yep. So our universe has these 3 characteristics. It has a width and a height, and then it has all these cells that are represented in this vector. Have I missed anything?
I think you're good.
Okay, cool. So to access the cell at a given row and column, we're going to translate the row and column into an index into the cell's vector. And we talked about that earlier with that row times width of universe plus column, I believe it was. Okay, Jagger prefers angled brackets. I like pointy brackets. I'm going with pointy. So okay, we need Wasm to go between Jagger and me, right? Like we would to go between Rust and JavaScript. So in Jagger language, they are angle brackets, and in Laura language, they are pointy brackets. Okay. So right, so we're going to use that row. Here we're going to have to, and this is starting to look almost Python-y, where we start having the self. So we've got that we're implementing this universe, and we're going to have this function that's going to get the index of a particular cell. And that's going to take itself as an argument, and then the row, and we're defining that the row will be of size U32, and then the column, same thing. And then that is going to return data of U's of type U size. And we looked this up yesterday, and I don't remember the result. I think it was variable.
I think from what I understand, we're essentially telling the Rust compilers, like, do you know what? Use the native architecture of my computer, the native architecture that I'm compiling to determine what the size of the number should be. I'm not really fussed. It can be 32, 16, ideally not 8-bit. That means you have an 8-bit processor, and that's a bit, I think, a bit old school.
Yeah. Okay. Yep. And so we're going to return that row times the width of the array representing the universe plus the column.
Yeah.
Okay, cool. And so what that'll do is give us the index of a particular cell in the universe that we are interested in, which will come in handy.
Nice.
And then we need to calculate the next state of a particular cell. And so we need to get a count of how many of its neighbors are alive. So we're going to write a live neighbor count method to do that.
And this is looking chunkier now.
Chunkier?
Yeah. Like the amount of code that we're
writing. Yeah. All right. So to this live neighbor count function, we're going to pass it the self and the row and the column same. And this time we actually are specifying the size that can be returned here. It has to be of 8-bit size. And so we're letting mut count equal 0. Why is it mut?
That's a Rust thing. So by default, all variables in Rust are immutable.
Okay. So this one, wait. Okay. So by default, so what we're saying here is that we want this to be mutable.
Yeah.
And that means that we can change it. So if it's immutable, then that means it has to just stay exactly the same. But if it's mutable, then it can change based on our needs, which is good because it's counting stuff. And so we would not want to create an immutable 0 because then we would never get anywhere.
Yeah.
All right. So we're creating a mutable 0 so that we can increment it. And we're going to have a delta row. So in our for loop, for wherever we are, whatever row we're in that, how much into the weeds do we want to get here?
I say whatever feels right.
Okay.
We are running out of time, and I'm afraid I'm going to have to hop off I do have a hard end at the top of the hour because I gotta go learn. I'm doing a course on dog care because I'm hoping to adopt a dog. So that means that I have to be there. Important. I have to be in class at 6 p.m. here.
Okay. So let's not necessarily talk about every character in our function that we're defining. We'll just give a 10,000-foot view of what this function is going to do. We're going to look at the row that our cell is in, and then that's going to be equal to 0. We're going to keep going if that's true. However, if it's not, then we need to count up our neighbors and see how many of them are alive. And the ones that are alive are all 1s. So then we're just going to add all of those up. And then we're going to return that as a count of size 8 bits.
0. Then we continue. Otherwise, we are getting the neighbor. Typing out the American spelling of neighbor is really throwing me out. Sorry, the US American. Sorry. So I think in Canada they also do the putting the U, right?
Yeah. Yep. It's just the states.
Yeah.
And I grew up, so my parents are Canadian, and I am also a Canadian citizen, but I have always lived in the US. And so there are words that I spell with the everybody but the states spelling, and then there are words that I spell with the states spelling. I don't like endeavor. I cannot spell that without a U, but color I don't spell with a U.
Oh, interesting.
So yeah, it's like whichever one I was somehow one of them made more of an impression on me than the other. Yeah, so I'm all over the place.
I mean, it makes writing CSS easier.
Does it?
Yeah, because CSS is in US English, right? And so like occasionally you'll see like tweets from British or Canadian CSS developers who are like, every time.
Yep.
We count up the number of cells based on their value, and this is where having that 0 or 1 value of it helps.
Yep.
That we can then sorry.
Yep. Yeah. So we end up with our count of our live neighbors. So now we have, for each cell, we can get its index and we can count up how many of its neighbors are alive. And that is pretty much all of the information that we need, right, in order to determine what happens on the next tick, the next generation.
Yeah. We just got to write out the rules, and and I just noticed here that the modulo, correct me if I'm wrong, we're using the modulo here so that we can wrap around the universe.
That's right. Yeah.
Gotcha. That's a phrase I never thought I'd say out loud. Wrap around the universe.
Yeah.
Makes sense. In that case, seeing as we're approaching the top of the hour, we got to keep going,
Yes.
Laura. Yeah.
Yes.
Let's see if we can get this going again. Because we gotta finish our game of life. I feel like we're building up the anticipation. I think we can get this done in one more. What do we like?
I think we can too, because it's just the rules next, and then
there's the rules and sorry.
Go ahead.
I was just gonna say there's the rules and exposing it to the browser.
Right.
So compiling and then letting the front end handle it. And then I think because we're first gonna represent it as a string, and then we're gonna represent it as a canvas.
Right. Okay.
But no spoilers. We'll get to that next time we get on this.
Yep. Yeah, these are super fun.
I'm glad. Yeah, same. Well, thank you, Laura. That was wonderful.
Yeah, thank you. And have a great time at puppy class, dog class. Yeah.
Yeah, and to everybody watching, thank you so much for joining. And catch you next time. We're doing these on a weekly basis, so we're very likely going to be here same time next week.
Last time was 2 weeks.
Yeah, sorry. We did one with Flaky last week.
Oh, gotcha.
So so as Suborbital, we're doing streams every week, but I still got to figure out what we're going to do next week because I'm hoping to have a different session set up, but it's kind of looking like we got to do these more often maybe. But I'm not going to promise that live. We'll figure something out.
Okay.
Thanks everyone.
All right. Thanks everybody. See y'all soon. Bye-bye.